Today we are going to be going over the value of openness. The goal of today's lecture is to teach you about principles of reproducibility and the value of adopting open science practices for your data science work. Now, the lecture assumes that you've read Goodman et al., What Does Research Reproducibility Mean? Sanvi et al., 10 Simple Rules for Reproducible Computational Research. It will help, although it's not necessary, to also read Gilmore et al., Progress Toward Openness, Transparency, and Reproducibility in Cognitive Neuroscience. If you have not read these already, please pause, go read them, and come back. Today's lecture is going to focus on three major topics. First, the types of reproducibility. Second, open science. Third, rules for reproducible data science. Let's start at the beginning. Let's start talking about reproducibility. Reproducibility is one of the ideals of science, and reproducibility means a true phenomenon or effect will be observed again under the same or similar conditions. The idea being that if something is real that you observe, you should be able to observe it every time in the same proper contexts. Every time I look out on the horizon in the east in the morning, the sun will come up. It's a reproducible observation. The other ideals of science include transparency. Conditions should be clearly defined such that others can reproduce any finding. And openness. Findings should be effectively communicated. Now, transparency and openness are actually just two ideals that serve towards the goals of reproducibility. If you are transparent in your process and open and effective in your communication, you should foster reproducibility of effects. Now, what is actually reproducibility in practice? It is not a unified concept. It is not a singular entity. It is actually an entity that reflects different types of reobservations or different types of replicability. So let's look at the different types of reproducibility that we have in science. I'm going to do these elaborations on reproducibility by going over sets of problems that lead to impairments in reproducibility. So the first problem that comes up time and again is that variations in pipelines leads to variations in results. This was quite clearly articulated in this 2019 paper by Botvinnik-Nezer and colleagues, who found that when they gave a set of labs, 70 independent laboratories, the same fMRI data, and asked them to just analyze the same tasks using the pipelines that are developed in those 70 different labs, they found a wide degree of variability in the results. So that even though the groups were working with the exact same data and had the exact same analytical goals, there was substantial variability across groups just as a result of the slight variabilities in their pipelines. So every region you see here in red highlights an area where you got much more variability across groups due to slight differences in their analysis pipelines. Now, this leads to a type of reproducibility problem known as methods reproducibility, which is independent investigators should obtain the same results when using the same methods as used in a previous study. Methods reproducibility relies on the fact that if you have effectively conveyed the tools and approaches, applying the same methods should give you the same output. Now, a solution to problems of methods reproducibility is simply share every step of your process from raw data to final figures. So the idea here is being as transparent and open as possible with your pipelines and your data. It should be able to help others reproduce those methods in their own labs. Another problem that comes up a lot is uncontrolled sources of variability can lead to dramatically different findings, even when using identical methods. This is probably most clearly highlighted in this widely discussed paper in 2015 from the Open Science Collaboration Initiative, where they tried to reproduce a set of established psychological findings from cognitive psychology and social psychology and developmental psychology, I believe, and see how often they could recreate the results of those effects, how often they could reproduce those effects. And what they found was that even though they were using the same methods as reported in the original paper, they got a vast difference in either the direction or the magnitude of the results. There was substantial variability in the results that they observed. This is known as a results reproducibility problem. Now, results reproducibility is the ability to obtain the same results from independent experiments whose procedures are as closely matched as are as closely matched as possible. So if you're given the same recipe, can you produce the same thing? And if you can't, you have variability or you have reduced reliability in the reproduction of your effects. And a proposed solution to the problem of low result reproducibility is the standardization of data types, architectures, and quality assessments for sharing data across research teams. The idea being that if you have standardized data types and architectures, your data is in the same format, they use the same integer types and character types and file formats, and the file names are the same, as well as you vet for data quality in the same way, that you should, by and large, be able to produce the same results. You should get the same effects. Now, even if you use the same methods and you apply them and start to get the same results, there's another problem that can come up with reproducibility, which is that variability across studies will lead to different conclusions from the same set of findings, which means that people looking at the same data will come to fundamentally different conclusions. This is most notably highlighted here by Barnes et al. In 1998, where they looked at how people interpreted the results of smoking and whether or not it was harmful to people's health. So this was a meta-analysis. And they found that there was a high degree of variability across studies that looked at the same data as to whether or not smoking was harmful to your health. So same data, same methods, yet the conclusions were vastly different across studies. This is known as an inferential reproducibility problem, deriving the qualitatively different results or qualitatively different conclusions from a set of similar studies or a replication and reanalysis of the same study. In some ways, it's like the three blind men looking at the elephant. One feels the trunk and says it's a snake. One feels the ears, thinks it's a bird. One feels the legs and thinks it's a tree. They're all looking at the same thing. They're just coming to different conclusions. This is a harder problem to deal with in the field. And often the solution is the use of meta-analytic techniques and the incorporation of rigorous statistical analyses, including machine learning that can aggregate across studies in order to find reliable directions and magnitudes of effects. So we have the concept of reproducibility expanded out to methodological reproducibility, results reproducibility, inferential reproducibility. And at every stage, we can find problems in the scientific culture of attaining reproducible results. Now, there is a movement designed specifically to address this. This is known as the open science movement. I'm just going to refer to it as open science. In general, it's more of a philosophy now, or an ideological approach to science than it is now a movement itself. And to understand what open science is, you have to take a step back and look at the history of science overall. Now, the way that we approach the modern scientific method goes back to about the Enlightenment era in Europe. Although there is a history of empiricism and scientific discovery that goes back even farther into Islamic empires and other civilizations out east, but it really kind of consolidated and was amplified thanks mostly to the printing press in the 1600s during the rise of the Enlightenment. Now, science really exploded as a result of the ability to communicate findings. So with the advent of the printing press, better transport systems to move printed documents across long distances, you started to see expansion of communications of science. And the way the science was communicated was restricted largely to written mediums. So mostly journal articles or in-person conferences. So people would either meet and present their work and talk about their work, use demonstrations in large public arenas, or write them down in as journal articles, which really didn't start until the 1600s, 1700s. So as a result, there was a limitation in space and access. It was very expensive to print at the printing press, so you wanted to communicate your results as efficiently and effectively as possible. You had to reduce the amount of space on the printed page. It was restricted to people who could travel, who could meet in these groups. And really, verbal communication, either spoken or written, was the primary medium of conveying your methods and your findings. Now, this really started to take hold in Europe and progress throughout Europe and the world as we got better mail systems and transport systems, but it didn't really fundamentally change in structure until the rise of the internet. Now, the internet's been around since before the 1990s, but it really started taking off in the 1990s. And as a result of the internet, we now have electronic mediums by which to communicate our methods and our results and actually give our data, physical data, to other people. So the medium shifts from continuing written journal articles and in-person conferences, but now you have recorded talks, blogs, markdown notebooks, online repositories, etc. By shifting to an electronic medium, this allows for a removal of the space constraints that you have with physical printing. It makes you more accessible to people all over the world. Most importantly, it allows for the direct transfer of your methods and your data. We can share our analysis scripts. We can share our actual data. We can make a digital copy of our data, and we can instantly give it to somebody anywhere else in the world. So a lot of the practices that we still currently do in science were solidified prior to the rise of the internet. But over the last 30 years, we've seen this shift in our ability to push our science farther and faster. But it requires us rethinking our approach. We haven't fully adapted our approach to the process of science to meet or take advantage of these new mediums. And the goal of open science is to really leverage this new medium. So the open science movement is defined as the movement to make scientific research and its dissemination accessible to all levels of an inquiring society, amateur or professional. So the fundamental idea is to increase the access to the process and products of science, move it out of the laboratory, and give it to anybody who is interested in actually working with the methods or the data. This is a fundamentally different way of thinking about doing science than we've done for hundreds, if not thousands of years. And as a result, it's still kind of in its infancy, although it is much more widely adopted than it was even 10 years ago. The nice thing about the open science movement is that it's fundamentally focused on increasing that key value of the scientific process, increasing reproducibility of findings and effects through openness. And this was the major point of the Sanvi et al. Paper, where they distilled the process of open science practices into 10 very easy principles that serve as kind of a conceptual bedrock for how to execute open science. And the goal for this data science class is to teach you the open data science practices that allow for you to effectively share your tools. So we're going to learn these techniques in the process of learning how to do data science, because you can no longer think about doing data science without leveraging open source or open access materials. Okay, so let's go over the rules for reproducible data science. First rule is, for every result, keep track of how it was produced. Look at the analysis workflows, carefully specified pipelines, setting up shell scripts, make files, etc. The idea is you should have a log or a history that keeps track of every step from your rawest of raw data to your polished final figures in your papers or your talks. Having this record of the steps along the way and being public and open about it gives anybody else who wants to replicate it that nuanced understanding of the process by which you executed your work. This includes yourself. One problem that happens a lot in the research lab is that people fail to replicate their own work because they forgot steps along the way. A classic example of this is the discovery of acetylcholine. Acetylcholine was discovered in the middle of the night when a scientist had an inspiration in his dream. He woke up, wrote it down, went back to bed. Immediately woke up, replicated it, and discovered acetylcholine. He communicated his result in a limited fashion to his colleagues, who discovered they couldn't replicate the effect. It was because he didn't write down every minute detail, including the critical detail of the temperature in the room. And it turned out his chemical discovery of acetylcholine relied on a very specific cold temperature, where he was working in, I think, Germany in the winter. And when his colleagues were trying to replicate it in the summer in France and England, they couldn't because it was too warm. So every minute detail you should think of, because you never know what detail is going to be critical for people to replicate your work. Principle 2. Avoid manual data manipulation steps. Script everything. Automate everything. Use standard functions. If you can't script something, or you can't put something in an open script that you can pass along to somebody else, let's say you're using proprietary software or what have you, then you should at least have extensive documentation of the manual steps that you cannot avoid. So if you can't pass along a script or notebook of every step that you took, automated step that you took, and you had to do some manual steps, be detailed in what those steps are, which relates back to point number 1. Next, archive the exact versions of all external programs used. Record your version numbers. Use Dockers and containers, which are now available, so you can basically freeze all of the libraries and versions of the software you're using into a isolated little virtual machine that you can pass along to others. So they don't even have to have the same software installed on their computer because everything's packaged in the Docker or the container. If you can't do that, you should at least have documentation of what version of software you're using. So for example, we're going to be using R in this class. So use and state the version of R that you use to generate your code, 4.0.3, let's say. If you're using libraries, note which versions of the libraries you're depending on and using. Next, rely on version control for all custom scripts. Now, version control through things like Git or Subversion are databases and repositories where it takes a snapshot of your code and your data, and every time you update it, kind of archives the last version. So you have a history now saved of how your code and your data changes. So if anything happens and you have to take several steps back, you automatically have that saved. In this class, you're going to learn a lot about how to work with Git and GitHub. It is probably the most common version control method used in data science. But there are others out there. And the key is to have this clean documentation and capturing of the versions of your scripts. So people can kind of see the history of the development as well, and you can go back in the history of the development as well. If you don't use version control as an automated software, use version control manually, which means that zip or archive the current version of your code when you want to make a new development, push that off to the side, and start version 1.0. And then version 2.0, then version 3.0. And each time you want to make a big code development leap, archive it and push it off to the side. It's more manually intensive, but if you don't want to work with version control software and scripts, that's the next best thing you should do. 5, record all intermediary results when possible in standardized data formats. Now, what do we mean by that? Data analysis is a multi-step process. There's usually tidying of your data table. There's data cleansing we're going to go over. Sometimes you're going to have to do some transformation of data or construction of new variables. Each step produces a new version of your data. And you want to be able to save or at least archive those intermediary data steps. So for example, you might start with your raw data in a tab delimited or comma separated file format. You might then use R or MATLAB or Python to pre-process your data, to tidy the data table, consolidate across data files, cleanse your data, and then you save that out as a new type, let's say, like a binary data type like R or MATLAB. Then you might run a first level analysis. You might get the means and standard deviations and look for a simple regression analysis across variables. And you might want to save that output, and your data might have residuals for every observation that gets added to the data table. Make that a separate data file, and so on and so on. So that way, you not only have access to the scripts that generate this pipeline from raw data to final data analysis, but you also have the actual reprocessed data itself. And this is very important because minor steps in the data that's saved can be replicated. Whereas, let's say that you don't version control all your scripts that you work with or all the software that you use, you upgrade R or you upgrade a library, and then you just try to run the same script on the same raw data, you will get different results. That was the key part of that study that I showed at the beginning, where people using slightly different pipelines got dramatically different results on the same fMRI data. 6, for analyses that include randomness, let's say permutation testing or bootstrapping, note the underlying random seed. This is one that people often don't do or forget to do. We actually cannot, as humans, create randomness. Nothing is really random. Computers are deterministic systems. So when we want to do a random number generator in order to generate noise or permute our data, we aren't actually using true randomness. We're using a random number generator that starts with a seed number. So you need to record what that seed number is and track it. Because if you run the same random number generator with the exact same seed, you will get the exact same random set of numbers, which aren't really random. You'll get the same numbers, the same results. This is two functions here, really. One is so that people can actually, if they want to do permutation analyses just the way you did, they can get the exact same results you got. Two, it'll help you keep track of cases where you're actually not working with random numbers. One common mistake that occurs in data science is trying to do something like a permutation test across variables, but using the exact same seed over and over again. So what you think are supposed to be different permutations of your data actually end up being the same permutation repeated over and over and over again. So if you're going to use randomization, note your seed. Next, always store the raw data behind every plot. Every plot's going to be generated from a particular data table, particularly summary of observations of variables. And you're going to use that subset of your data or processed metadata to generate a plot, a scatter plot, a heat map. Be able to store that. Now, many modern plotting tools in Python and R actually store the data behind the plot. So if you want to make a scatter plot of 100 points across two variables, embedded in the saved plot itself will actually be the arrays that were for X and Y. So you actually have that embedded into the plot. And so a lot of modern plotting software will do that for you. But if you're not, be sure you can save that. And one thing that we always try to do in my lab is actually have a set of scripts, or in this case, a Jupyter notebook, that walks people through generating every single figure from your paper, so that anybody can download, at least take the process data behind each plot and make the same plots that we produce in the paper. Next, generate hierarchical analysis outputs, allowing layers of increasing detail to be inspected. Now, what do I mean by that? Well, basically, it's a combination of item number 5, which is record all intermediary results where possible, and item 7, which is always storing the data behind the plots. If you save each step in your process from raw data to final output, and you record the actual data that goes into the final visualization of your plots or your statistics, you will be able to achieve automatically 8, which is the hierarchy of the analysis that leads to your final results. So 8 is really just a special case of steps 7 and 5. Next, connect textual statements to underlying results. You want to be able to have the reader link things that they're reading as either the text on a Jupyter notebook or in a paper with the visualization, either as a table or a plot, of that result. You want to have this symmetry between the two, and you want to have them immediately connected. So you want to learn how to put this in the caption, or if this is the value using markdown notebooks like Jupyter, you can have a text statement that's linked right above the code that's used to execute a plot that shows the result that you want. So you want to be able to keep the conclusions in the context of the data that leads to them. And this proximity makes it easier for people to not go through conceptual leaps for interpretation and reduces the inferential reproducibility of your work. Finally, provide public access to scripts, runs, and results. When possible, make everything open and shareable. Share your raw data, share your pre-processed data, share the scripts that got you there, share the code that generates the plots and saves the exact same plots you got. Everything should be out in the open. Now, in the era of pre-registration, you even share your initial hypotheses before you started working with your data. Make everything as public as possible. So in this class, you'll learn how to use GitHub and public GitHub repos along with Jupyter notebooks so that you can store your data and your scripts and your markdown notebooks that allow for you to generate these findings in a conceptually easy to understand manner and make those accessible to the world. So anybody can clone your repo and recreate your work. Now, in some cases, you can't do that. There are data restrictions for certain data collection efforts, or there are sharing agreements for some data. We're not completely open yet, and some of you might be working with data that's not shareable. But you should be able to share some portion of it. The processed data that went behind each plot, that should be something that you should be shareable because it's something you're giving to the world anyway. So as much as possible, make everything public and open. And if you follow these 10 steps, you're fundamentally achieving the goals of data science, right? You are fundamentally achieving this open practice, which increases the reliability and reproducibility of your work. So in order to kind of meet those 10 goals of reproducible data science, you want to think about the tools, and we're going to learn these tools as we go through this class, that are going to help you achieve this. So I recommend using open source software. This includes R, Python, Julia. This is different than saying open source code. So MATLAB is a closed source software. You have to pay for a license to use MATLAB. Whereas R and Python and Julia, you don't have to pay for the software itself. That's freely available and publicly developed. Use flexible IDEs to develop and organize your code and scripts. An IDE is an integrated development environment. So for example, in this class, we're going to use RStudio. It allows for you to integrate the development of the code with a text editor, an interpreter, or a command prompt that allows for you to execute the code, controls your plots, your markdown rendering, things like that, all in one interactive environment. And you want to use this because it helps you think about the process of working with your data in a holistic way, as opposed to a script that you separately then run on a command line, then you have to open up the plots through a Finder. Everything should be developed in a kind of flexible IDE. It's also really useful for debugging because a lot of IDEs that you'll use, particularly RStudio, allow for you to pause your code so you can stop around a bug and try to figure out what a bug is. Use markdown notebooks to summarize your investigation. So we'll be using Jupyter in this class. There's also R Markdown if you're just exclusively using R. These are effective ways of just tying, again, the textual results, the verbal inferences of your results with the code and the results that are pulled from your data. So you can have the text that tells the reader what they should see, and then a code cell that implements a code that generates a plot. And all of that now ties everything nicely together in an easy to summarize way. So it's a very powerful way of communicating the findings that you're getting. Use version control software like Git or Subversion. We'll be working a lot with Git in this class, which is pretty intuitive to use, but get comfortable with using version control. So that way you can track and monitor the progress of your pipeline as you develop it. Most importantly, if you use Git, you can also push things to public repos so that you can share, which is the last kind of item here. Use public repositories for sharing data and code. And this includes GitHub. We'll do a lot of work with GitHub. If you have files that are particularly big, you can use something like Figshare, or if you're at Carnegie Mellon University, KiltHub, which are ways of posting large data sets that gives them a DOI, a number for identifying, a documented number for identifying that data set. So you can publish large data sets and then link them through GitHub. Using these practices will guarantee that you're following the principles of open data science, which in turn allow for you to more accurately achieve the goal of reproducibility in your analyses. So if you take anything else away from this lecture and the readings, I want you to see that adopting practices of the open science movement allows for achieving the goals of science in general and data science in particular. And I'm going to make the argument that it's incorrect to think about the contrast as being the practice of science versus the practice of open science, which is traditionally how this is framed. I think we've made a good case that open science practices serve the fundamental goals and ideals of science. So instead, I'm going to argue that the contrast should always be thought of as science versus closed science, because fundamentally, openness and transparency are the core ideals of science. And what you're going to be learning in your practice of data science in this class is this ability to maintain open science practices in order to have your results be as reliable and robust as possible. Take care.